By this point it should be known that I really enjoy robots with tank treads. And I've already built 2 of those, so I wanted to try something different. And instead of using Arduino as I have in the past, I wanted to use the Raspberry Pi. I'm Caden from Kepler Electronics, and let's get started. In case you've been living under a rock for the past few years, the Raspberry Pi is an inexpensive computer. It runs a flavor of Linux and can do everything that a normal computer can. It includes Wi-Fi and Bluetooth built in, both of which are extremely useful. Using the Raspberry Pi also allowed me to play around in the Python language, which is something I've been wanting to learn about for quite a while. Now, if we want to use motors, we need to use a motor controller. And the motor controller I chose for this project is the Pimeroni Explorer Hat, which is meant for the Raspberry Pi Zero, but is one of a surprisingly few number of motor controllers that are built directly for the Raspberry Pi. I purchased these stacking headers, which will allow me to still access the pins when the hat is in place. All of this is mounted to a Prololu expansion plate with standoffs that are marketed as being specifically for the Raspberry Pi. The chassis for this project was a cheap chassis ordered off eBay, which had some issues, but it was much cheaper than any alternatives. The motors used on the chassis have 2 Hall effect sensors built in, so that's what the extra wires here are for. I ended up soldering on some extra wire for added length. The black wire is the motor power and red is the motor ground. Yes, it seems backward, just go with me on this one. The white wire is power for the encoder and the yellow wire is ground for the encoder. And the orange and green wires are the encoder signal wires. We don't care about any of the encoder functions for this project, so I just kind of stuffed them under the expansion plate. The whole device is powered by a portable USB power bank, which has plenty of juice to power it for a while. Since I really enjoy controlling my robots with gamepads, I decided to use my 8-bit DOE SF30 Pro. It's a Bluetooth gamepad that works with Mac, PC, Android, and the Nintendo Switch. It doesn't advertise working with Linux, but pairing it using Android mode works extremely well. Each pairing mode actually appears as a different device with the same name, so be sure to pair it in Android mode. Before pairing, run this command, which will spit out a number of events, which are actually the keyboards, mice, and gamepads currently connected to the Raspberry Pi. Pair the gamepad in Android mode by holding B and start before hitting the pair button and holding it. After pairing, a new event will show up. This event number does depend on how many things are connected before this one, but we'll come back to this later. Write down the current device number. We'll use this for testing before we finalize things. One of the critical libraries for this project is Evdev, a library that allows you to read from things like keyboards, and specifically in this instance, it allows us to read from gamepads. We run this command to install Evdev. After we ensure that our controller is plugged in, we can run this example program, which will show you everything that is coming from the controller. Button values are shown as EV_key, whereas the analog sticks are shown as EV_ABS. Interestingly, the D-pad is also under EV_ABS, which is pretty interesting. If you want to use different axes for movement, or if you want to use buttons to accomplish another task, this is where you would find the codes for each button. Interestingly, the joysticks are mapped in the inverse way that you would expect, being that when the joystick is pulled all the way back, it's giving a value of 255, and when it's pushed all the way forward, it gives a value of 0. Keep in mind that you will have to use this program to find out what your specific controller calls each button, because chances are that your controller model won't have the same mapping as mine does. The IDE, or code editor that I'm liking, is Thonny, which is built into Raspbian, which has a built-in function for searching and downloading libraries, so let's do that first. After making sure that the Evdev library is installed, we have to install the Pimeroni Explorer Hat library, which allows us to control the motors. This leads us into the code, which I have uploaded to Dropbox if you want to take a closer look. We start by importing the Explorer Hat and Time libraries. The Explorer Hat library allows for motor control, while the Time library allows us to do delays and wait commands. We then invert one motor, because the motors are aligned inversely to each other on the chassis itself. We then import the input device and E-codes components from Evdev, which allows us to actually read from the controller. We then use a while loop to try opening event 0, which is the event code for my controller when nothing else is connected. If this doesn't work, it prints to the console and waits for 1 second before trying again. Once the controller is found, it prints that out and sets event 0 as the gamepad. Printing gamepad also allows us to see the info about the gamepad, such as its name and identification number. Next, we look for events, button presses or joystick movements, in a loop that constantly checks what is pressed. I first check to see if the event type matches the EV_ABS type, which returns an absolute value. In this case, meaning an analog stick value. If the event code is 5, that means the right joystick has been moved, and we then choose to move motor 1 forwards or backwards depending on what value the stick is sending. I have a dead zone where the joysticks aren't controlling anything between value 100 and 155, which cancels out joystick drift, allowing us to keep the Rover still when we don't want it to move. We map the joystick value onto the motor speed, which allows us control over the speed of the robot depending on how far the stick is pushed. We have to do some manipulation of the data here because the motor controller library only accepts values between 0 and 100 for the speed of the motor. This is relatively simple. To do so, we simply subtract 155 from the high range to keep the range between 0 and 100. On the lower range, we subtract the value from 100 to invert the range, because even though the values are within the range, it is inverted from what you expect. We also have an else statement that makes sure that if the joystick value is between the values we use to make the motors move, we stop the motor so it doesn't drift. For the left joystick, we use the exact same code, but we changed from event 5 to event 1, which is just the identifier for the joystick. Again, this won't necessarily be the same event codes for your controller, so be sure to check it using the method we outlined above. One thing that is very important is running the program at boot, which allows us to use the Rover without having to plug in a keyboard, mouse, and monitor. The first thing you'll want to do is save your program to the /home/pi directory. We must then open up a terminal and type in this command, which will open up the .bashrc file with the nano text editor. We must then scroll to the bottom before adding in the location of the file you want to run. Press Ctrl and X to exit, press Y to save, and press Enter to save the modified file at the same location. After saving, reboot the Pi to see if it works. If it doesn't work and you need to run some commands, press Ctrl and C at the same time to exit the program. This method of modifying .bashrc also runs the program every time a new terminal is opened. Assuming you don't want to keep a keyboard and mouse plugged into your Raspberry Pi at all times, you will want to change the event number in this line right here to event 0, which means that it is the first device connected to the Pi after startup. I would recommend changing this at the end after you have tested the code. I would click reboot, unplug everything, and then wait for the Pi to start up. After you see the terminal, I would press the button to connect your controller, as the Pi is already searching for it. If your robot has something else connected at startup, you may need to change it from event 0 to event 1 or something else. Overall, the robot's pretty cool. The chassis certainly has some issues, and the motors aren't super powerful, but you can still have some fun. I mostly wanted to try out some Python programming, which is a language that I really want to get better at. If you use a different chassis with some stronger motors, you could have a pretty fun time. I hope you enjoyed watching this. This project is a lot more of a programming project when compared to my usual projects, and I really enjoyed doing it. This project was also interesting because there wasn't a lot of information on how to use this library, so a lot of things I had to figure out for myself. I hope that this video is useful for you, and a lot of the resources I used to program this can be found in the description in case you want to look at them for yourself. Thanks a lot for watching, and if you want to check out some of my other projects, be sure to check them out here. Or, if they don't show up for you, check the description. One of my more recent projects is Blastwave, a 1-pound combat robot I'm building. Thanks again for watching, and if you have any questions, be sure to put them in the comments down below. If I can, I'll try and answer them for you. Thanks for making it this far, and keep designing.